Okay, let's unpack this. Today, we're doing a deep dive into something really shifting the paradigm, I think, in autonomous AI agents. We're focusing on WebSailor v2. It's an open source agent developed by Tongyi DeepResearch that's part of Alibaba Group. Now, for those of you really embedded in machine learning data science, this paper presents a crucial technical story. We're here to dissect exactly how this moderately sized open source model, it's a 30B, A3B mixture of experts, and MOE is managing to close that huge performance gap. You know, the gap that's always separated community models from the big proprietary systems, like the ones from OpenAI Deep Research or Gemini.
Right. And our mission today, it's explicitly professional, comprehensive. We want to get beyond just the headline numbers. We're aiming to convey the, let's say, intrinsic value and the real technical contributions of this whole post-training pipeline. We'll explore the methodology, the innovations in the data, which are quite something, and the solid engineering decisions that, let them achieve this. We're assuming you've got the ML expertise, so yeah, we're diving straight into the deep end of the architecture.
And it's quite an architecture, isn't it? The headline result, well, that's what should really grab your attention, especially if you're an engineer in this space.
Yeah.
WebSailor v2 hits state-of-the-art for open source agents. It scores 35.3 on BrowseComp EN, that's a complex benchmark, and 30.6 on Humanity's Last Exam, or HLE. But what I find genuinely remarkable is the size-to-performance ratio. I mean, this 30 billion parameter agent decisively beats the much, much larger 671 billion parameter DeepSeek v3.1.
Right.
This isn't just a win, it feels like a categorical validation that, sophisticated data engineering in a really well-designed training environment can actually overcome raw model scale limitations.
That ratio is the defining challenge, I think, for the open source community.
That's
And yeah, this WebSailor v2 paper basically provides a detailed blueprint for tackling it.
Okay, so let's start with the bigger picture, the strategic context. The whole pursuit of AGI, it really hinges on creating truly autonomous agents, agents capable of what they call deep research. Which means, moving beyond a simple Q&A, they need to leverage external tools, iteratively retrieve information, synthesize it, perform complex analysis, and that's exactly where the major performance gap has been.
Exactly. And what the authors recognize right away, and what we should really appreciate, is the core performance bottleneck in these open source systems. That persistent gap compared to proprietary models. It boils down to two critical interconnected challenges. The first one is data. Open source efforts, well, historically, they've relied on pretty limited data diversity. And crucially, they often suffer from these monolithic definitions of uncertainty.
Meaning?
Meaning they often just rely on simple obfuscation, like hiding a key detail to make the task harder. But that doesn't really capture the kind of structural ambiguity you find in real world knowledge.
Right, okay. And the second challenge, that's the cost and volatility of the training environment, right?
Precisely. Training these agents, it requires massive rollouts, high concurrency, and every step involves calling external APIs, search engines, web parsers, code interpreters. This introduces just unavoidable randomness, stochasticity. You get high latency, you hit QPS limits, APIs fail, outputs aren't consistent, and all this volatility. It contaminates the training signal, it drastically hinders scalability, and it makes getting robust reinforcement learning policies to actually converge incredibly difficult.
Okay, so WebSailor v2 is designed to tackle these really deep-suited problems head-on with a full-stack solution. It sounds like it's organized into three main stages.
That's right. First, there's the innovative data construction pipeline they call Sailor Fog QAV2. Then policy initialization using supervised fine-tuning, SFT. And finally, refining that policy through reinforcement learning, RL.
So digging into the agentic core, they made a pretty interesting choice building on the React framework reasoning and acting, especially when you see others going for more complex setups.
It is fascinating, isn't it? You see a lot of push towards complex multi-agent systems or elaborate planning modules like Tree of Thought, but the WebSailor team, they deliberately chose React. And they explicitly connect this choice to Sutton's The Bitter Lesson from back in 2019.
The idea that general methods leveraging computation scale better than complex, hand-engineered designs. So React is simpler, more general. They're betting on intrinsic capability over complex scaffolding.
That's exactly the core hypothesis here. By sticking with React, they avoid needing these intricate human-designed plans or specialized prompt engineering tricks. The focus shifts entirely to cultivating the intrinsic capability of their underlying MOE model. Mathematically, you can think of the trajectory $HT as just this sequence: thought, action, observation. The model's thought and action are sampled directly from its policy. The whole idea is for the policy itself to learn and internalize complex strategic reasoning rather than relying on some brittle external planning module that might break easily.
Got it. So let's quickly review the toolkit, the agent's action space. It looks like 4 main tools plus a termination action.
Yep, pretty standard set, but with some sophistication in the implementation. You've got search, which calls a standard search engine, gives back titles, snippets, URLs. Then, crucially, there's visit. Now, this one doesn't just dump raw web page text. It retrieves the content, sure, but then it actually uses the Qwen 330B A3B model, the agent's own base model, as an internal summarizer. So the observation returned is a summary tailored to the agent's goal.
That integration is interesting. Using the agent model itself to summarize observations, isn't there a risk there? Like introducing bias, or the agent may be hallucinating its own environment based on its internal summary? Or is the efficiency gain just too good to pass up?
That's a really sharp critique, and it's a valid concern. The paper doesn't explicitly address the hallucination risk head-on, but it implicitly justifies the choice by emphasizing efficiency and, importantly, context management. Think about it, they have a 128K context window. Sending compressed, goal-relevant summaries maximizes the useful working memory the agent has for long-term reasoning across many steps.
Right. Sending raw HTML would blow through the context limit instantly on complex tasks.
Exactly. So the alternative, feeding it potentially hundreds of thousands of tokens of raw code and text, would just overwhelm the context and guarantee failure on long trajectories. They seem to be making a calculated trade-off, except a low, hopefully controllable level of summarization bias in exchange for massive gains in task memory efficiency, which is essential for deep research.
Okay, that makes sense from an engineering perspective. And the other tools?
You have Google Scholar, obviously specialized for academic papers and sources, and finally the Python interpreter, which is a sandboxed environment for doing complex calculations, data manipulation, that sort of thing. So yeah, that full toolkit pretty much covers the bases for sophisticated deep research tasks. All right, now this part, Sailor Fog QAV2, this is where I think the core engineering innovation really shines. The paper puts forward this philosophy. Information retrieval isn't linear. It's not just following a path. It's more like navigating a really complex, high-dimensional web of entities and relationships. Therefore, they argue, the training data itself must be structurally rich. It needs to be rooted in a knowledge graph that actually mirrors that real-world complexity.
And they specifically call out the limitation of previous approaches, like their own V1 work, right? These methods that start easy and kind of iteratively expand, they tend to produce logical structures that are mostly tree-like or cyclic.
Exactly. These structures are simple, easy for an agent to traverse maybe, but they fundamentally fail to represent the loops and interdependencies you find in real knowledge.
Okay, can you give an example of that kind of loop?
Sure. Think about a complex legal research task, or maybe financial due diligence. You find entity A, which points you to document B, but document B only makes sense if you verify fact C from a different source. And maybe fact C has some conditional dependency that loops right back to a specific attribute of entity A you saw initially.
Ah, I see, like needing to confirm a date mentioned early on based on something found much later.
Precisely. Those are cyclic structures. And prior data generation methods really struggled with them because creating them requires nonlinear, almost recursive search strategies during data collection. So WebSailor v2's big innovation here is that during the graph expansion phase, it actively seeks out and establishes denser connections. It intentionally creates these cyclic structures. The effect is that it forces the agent during training to internalize logic for recursive verification, for backtracking, which is absolutely essential for handling the ambiguity and complexity you find in real-world research.
And they didn't just focus on the structure, they improved the metadata captured within the graph too.
Correct. They made sure to preserve crucial procedural information. Things like the exact search queries used, the source URLs where facts were found. Plus, they computed and stored statistical features for the entities, things like how often they appear or co-occur with other entities. And this metadata isn't just passive. It's actively used later to inform how they generate the QA pairs, specifically influencing the complexity and the type of uncertainty introduced.
Okay, so building this denser cyclic graph creates a richer foundation. But that structural innovation must have created a new problem during subgraph extraction, right? Trying to enumerate all possible substructures in a graph that dense and cyclic. That sounds like a combinatorial nightmare.
Oh, absolutely. That's the classic bottleneck. Exhaustive enumeration just becomes computationally intractable very, very quickly. You can't possibly list every single path or reasoning structure. So their V2 solution smartly pivots away from that. Instead of trying to find everything, they adopt a highly efficient, random walk-based approach for extracting subgraphs.
row?
But it's not just any random walk. It's carefully constrained to ensure they get topological variance. The goal isn't quantity, it's diversity of structure. They want to make sure they capture a representative sample of different reasoning topologies.
How do they actually verify they're getting that diversity, though? How do they know they aren't just sampling slight variations of the same simple structure over and over?
Good question. They use a well-established technique, the Weisfeiler-Liman algorithm. Think of it as a way to generate a unique fingerprint for the structural shape of each subgraph they sample. By applying this algorithm, they can check if their collected dataset contains a sufficient quantity of non-isomorphic connected subgraphs, basically, subgraphs with genuinely different shapes or structures. So, for our technically savvy audience, this check confirms they aren't just getting, say, 10,000 variations of a simple linear path. They're verifying they have truly distinct, complex reasoning patterns represented in the data before it even hits the training pipeline. It validates the structural quality.
Okay, that's clever. Now, moving on to the actual QA generation from these subgraphs, the strategy is to distribute focus evenly across all orbit nodes. What does that mean?
Right. Orbit nodes basically refer to nodes that occupy different structural positions or roles within the subgraph topology. Think nodes with many connections versus nodes at the end of a chain, or nodes within a cycle. By ensuring the QA generation process focuses evenly across all these different structural roles, they make sure the agent learns to reason effectively about different types of knowledge points within a complex structure.
And this is also where they tackle that monolithic uncertainty problem you mentioned earlier, moving beyond just simple obfuscation.
Exactly. This is a major step forward. Prior agents often failed because they were primarily trained to solve for one kind of difficulty. Obfuscation, where, a key name or date is just replaced by a placeholder like person or date. WebSailor v2 introduces a much wider array of defined uncertainties, going significantly beyond just hiding information.
Can you give us a flavor of what that wider array actually entails? What kinds of uncertainty are we talking about?
It really moves into the realm of semantic and logical complexity. So it includes things like temporal ambiguity, where a fact might change over time, forcing the agent to verify information within a specific date range. It includes conditional dependence, where fact X is only true if some other, possibly remote, fact Y is also confirmed. This forces multi-step verification. And critically, it includes multi-source conflict. This is where two credible sources might offer contradictory information about the same point, forcing the agent to evaluate source reliability, weigh evidence, maybe even seek a third source.
Wow. Okay. So that suite of uncertainties sounds much closer to the challenges a human researcher faces. It's not just about finding missing pieces, but about resolving ambiguity and conflict.
Precisely. This richer set of uncertainties is what compels the model to engage in more sophisticated reasoning, hypothesis generation, verification loops, rigorous synthesis. It's a key part of pushing the agent towards truly superhuman research capabilities.
All right, so we've got this robust base model, the Qwen3 MOE, and this incredibly innovative, structurally complex dataset from SailorFog QA-v2. Now let's talk about the training pipeline itself. It starts with the standard practice, SOT for a cold start, then RL refinement.
That's the sequence. And that SFT cold start phase is absolutely vital, maybe more so here than in other domains. The dataset used for SFT is entirely synthetic, generated exclusively from SailorFog QA-v2, the actual training trajectories. They're constructed by taking successful task completions generated by other open source models and then using rejection sampling to filter for high-quality examples. Another key detail. They significantly boosted the base model's context length for v2. The Qwen330B A3B Thinking 2507 model went from a 32K context window in v1 up to a massive 128K window here.
And that increased context, that's pretty much non-negotiable for these kinds of web-based agent tasks, wouldn't you say? The amount of information you need to track.
Oh, absolutely essential. You simply can't do deep, multi-step web research effectively within a small context window. But beyond just enabling longer tasks, this SFT phase serves a critical role as a prerequisite for RL stability. Think about web tasks. They are notoriously sparse reward environments. Getting the final answer correct might be the only positive reward signal you get after dozens of steps.
Right, lots of ways to fail, only one way to succeed.
Exactly. So if the agent starts the RL phase with a really poor initial policy, if it can't even perform basic navigation or tool use, it's just going to fail constantly. It won't achieve any meaningful exploration, it won't encounter those rare positive rewards, and the RL algorithm will likely just diverge or collapse.
So the SFT provides a strong enough starting point.
It provides a robust initial policy that's already capable of conducting meaningful long-horizon exploration. This ensures the agent actually encounters successes often enough to provide a sufficiently dense and reliable reward signal for the RL process to latch onto, stabilize, and ultimately converge effectively. It bootstraps the whole RL process.
Okay, that makes perfect sense. And this leads us directly into their really elegant solution for dealing with RL instability in this domain, the dual environment RL framework. Let's start with the simulated environment. The motivation seems clear: cost control, speed. But how did they ensure it was actually useful? How did they guarantee fidelity to the real world?
Right, the motivation was definitely cost, but also crucially determinism. Relying solely on live external APIs introduces that high operational cost, yes, but maybe worse for training stability is the highly non-deterministic stochastic nature of the real web. Their simulated environment is built from the ground up using an offline Wikipedia knowledge base. This makes it fully controllable, incredibly fast to run simulations in, and highly cost efficient. Now, the key to fidelity, making sure training in the simulation actually transfers to the real world, is how they populated it. They adapted the same Sailor Fog QAV2 generation pipeline used for the SFT data to create tasks and populate the knowledge within this offline corpus.
So the structural complexity and types of reasoning required in the simulation directly mirror the real-world target tasks defined by Sailor Fog QAV2.
Exactly. This ensures the interaction dynamics, the state transitions, even the reward mechanisms within the simulation closely mirror what the agent will face in the wild. This allows them to do really high-frequency algorithmic experimentation, data curation cycles, all without the noise and cost contamination of real APIs. It's crucial for getting that sim-to-real transfer to work.
But as you said, you can't train a web agent entirely in a simulation or sandbox. You need exposure to the messiness of the real web. So the managed real environment is essential for robustness. How did they tackle that inherent volatility, the API failures, the rate limits across that complex toolkit?
This, I think, is where the real system engineering genius of the paper comes through. They didn't just call the APIs directly from the RL loop. They architected a unified tool execution interface. Think of it as a layer sitting between the RL agent and the messy real world. This layer is managed by sophisticated scheduling and management logic, and its entire purpose is to create the illusion of a deterministic and stable environment for the RL training loop, insulating it from all that real-world stochasticity.
Okay, let's walk through an example. Say the agent decides to use the search tool, but the external SIRPI it calls returns a 503 server error, or maybe it hits a rate limit. What does this unified interface do? How does it maintain stability for the training process?
Great question. It employs a whole sequence of fault tolerance strategies. First, it has robust internal concurrency handling and adheres strictly to QPS constraints for each API, trying to prevent external service degradation in the first place. But if a call does fail, like that 503 error, the management layer automatically triggers timeout and retry protocols, maybe with exponential backoff. It tries again a few times. If the failure persists, the layer might then check its result cache. If it's made a similar successful call recently, it can immediately serve that known good result back to the agent. This avoids redundant calls and critically maintains the coherence of the agent's current reasoning trajectory.
So it papers over the transient failure using cached data.
Right. And if the failure is persistent, maybe the API is down for longer, or for non-critical failures, like maybe an image failed to load on a web page, it can execute graceful service degradation. Or it might even seamlessly switch to a designated backup data source if one is configured. The crucial point is, all of this happens transparently to the RL algorithm. The policy itself never sees the raw 503 error or the rate limit exception. It just sees either the expected result, perhaps slightly delayed, or maybe a slightly different but still valid observation, like text content without images. This ensures the training signal remains consistent and the learning process isn't derailed by random external events.
That deterministic buffering, that insulation layer, that sounds like the absolute key to making RL viable in this kind of environment. It separates stable training from just chaotic data contamination.
Absolutely. It's a huge engineering lift, but essential. And it all ties together because this entire system, the data generation, the SFT, the dual environment RL, is integrated into what they call a symbiotic data curation loop. Meaning the RL training dynamics, how well the agent is performing, where it's succeeding or failing, continuously feed back information to an automated data synthesis and filtering pipeline. So the agent's performance essentially dictates which parts of the Sailor Fog knowledge graph need more emphasis in the next batch of data generation, or maybe what specific types of uncertainties need to be surfaced more often. It's this co-evolution, this real-time optimization of the training data guided by the learning process itself that enables the rapid and continuous policy refinement they observed. Okay, so we have the setup. Now let's get into the nuts and bolts of the policy optimization itself. The core RL algorithm they use is a tailored adaptation of GRPO that's generalized proximal policy optimization, and it's optimized using a token-level policy gradient loss.
Right, and looking at the objective function they present equation 2 in the paper, it definitely has that PPO-like structure minimizing over a clipped importance sampling ratio. But the way they calculate the advantage estimate looks, well, different from the standard actor-critic setup.
It is. That's a key technical divergence worth focusing on. The objective uses the standard clipped importance sampling ratio, theta, to control the policy update size, just like PPO. But the advantage estimator is calculated differently. Instead of subtracting a learned value function from the return, it's defined as the trajectory return 3 the mean return across all trajectories in the current group or batch. So text mean G.
Why use the group mean return as the baseline instead of training a separate critic network to predict the value function of violars, which is the more common approach in PPO variants? What's the rationale there?
That choice speaks directly, I think, to the challenges of this specific agentic environment. In more traditional RL settings, a learned critic vial release works well because it can accurately estimate the expected future reward from a given state. However, in a super high-dimensional, non-stationary environment like the web, where observations are noisy summaries, the state representation is incredibly complex, and the world itself changes. Training a reliable critic function is notoriously difficult. It often struggles to converge, can have very high variance, or might overfit to transient patterns, leading to unstable advantage estimates.
Okay, so the critic becomes unreliable.
Exactly. So by using the simple group mean return as the baseline, they introduce an immediate, empirical, and much more stable statistical baseline for comparison within that specific batch of experience. It measures how much better or worse a particular trajectory did compared to the average performance right now. This helps stabilize the training update significantly without needing to rely on a separate learned function that might itself be unstable or diverge due to the inherent stochasticity of the web environment.
It's a pragmatic choice for stability.
Got it. And they maintain a strictly on-policy regimen, right? Always sampling with the latest policy. Plus, they use a leave one out strategy for further variance reduction in that advantage estimate. But let's talk about specific stability techniques they employ to prevent known failure modes. What exactly is this format collapse phenomenon they mention, and how does their conservative negative sampling approach address it? Right. Format collapse is a really common and frustrating failure mode when you apply RL to sequence generation tasks, especially with complex output formats like the React thought action sequences. What happens is, after training for a while, the agent sometimes discovers a way to cheat the environment or the reward function. For example, if trajectories that exceed a maximum length limit are heavily penalized, the model might learn that the easiest way to avoid that penalty is just to output a very short, possibly nonsensical or incomplete answer. It just terminates quickly.
So it optimizes for brevity to avoid the length penalty, even if the answer is garbage, effectively collapsing the desired output format.
Precisely. It sacrifices correctness and coherence for termination speed. Conservative negative sampling is their way to mitigate this. They selectively exclude certain negative samples from the gradient updates. Specifically, they ignore trajectories where the failure seems clearly attributable to hitting an external environment constraint like exceeding the maximum trajectory length rather than being due to a genuine failure in the agent's reasoning or action selection process.
I see. So if it failed just because it ran out of time, they don't penalize the policy for that specific failure.
Essentially, yes. By doing this, they ensure the gradient updates are focused primarily on correcting meaningful policy errors, bad reasoning steps, incorrect tool use, flawed synthesis, rather than just teaching the model to be arbitrarily short. It helps ensure the model continues to learn proper, well-formatted, and useful reasoning trajectories. They also noted, for efficiency, that they favored using larger batch sizes and group sizes within GRPO to keep the variance of the estimates low and provide adequate supervision. And interestingly, they opted not to use dynamic sampling techniques.
You know, this brings us right back to the bitter lesson again, doesn't it? The authors are pretty explicit in the paper, stating that the quality of the data and the stability of the training environment proved to be more critical success factors than the specific nuances of the RL algorithm itself. They even mention an experiment where they tried training the agent directly on human annotated data from the BrowseComp test set, and the results were significantly worse than training on their own synthetic data.
Yes, and that finding is perhaps one of the most profound technical conclusions in the paper for the broader community. Their argument is that even though human annotated data comes from complex real tasks, it's often limited in scale, noisy, and represents a training distribution that's too inconsistent and high variance for the agent to generalize from effectively, especially for learning intricate tool use patterns. The synthetic data, meticulously generated from their Sailor fog graph with its controlled complexity and uncertainty, provides a much cleaner, more consistent, and densely distributed learning signal. This allows the policy to internalize the fundamental reasoning patterns and tool use skills far more robustly. It suggests that for these kinds of agentic tasks, engineered data quality trumps real but noisy data.
Okay, let's cut to the chase then. All this complex data engineering, the dual environments, the tailored RL, did it actually work? Let's look at the performance numbers. Table 1 seems pretty clear. WebSailor v2, the RL-tuned version, achieved state-of-the-art results among open-source agents. That 35.3 score on BrowseComp EN really stands out.
It does, and it confirms that core finding we discussed earlier. This 30 billion parameter MOE agent genuinely surpasses the much larger 671 billion parameter DeepSeek v3.1. It's compelling evidence that their methodological approach can indeed overcome sheer model scale.
And what about the HLE score? 30.6 on humanities last exam. What's the significance there?
That HLE score is particularly significant, I think. HLE is specifically designed to test human-level scientific reasoning, academic problem-solving, complex logical deduction. Achieving a score that high strongly validates their underlying hypothesis that developing strong, tool-driven information retrieval and synthesis capabilities fundamentally enhances the model's core logical reasoning capacity. It allows the model to effectively reason over externally acquired, verified knowledge, pushing its performance beyond what its intrinsic scale might otherwise allow. The tools become an extension of its reasoning power.
Right. But before the RL refinement, we need to look at the impact of the SFT cold start alone. That intermediate checkpoint, just after SFT, already achieved 24.4 on BrowseComp EN and 23.9 on HLE. That's a massive head start before RL even begins.
It's a critical data point, absolutely. That performance level from SFT alone is already better than many other fully trained open source agents achieve on these difficult benchmarks. It emphatically proves the point we discussed. Having a highly competent initial policy, trained effectively on structurally rich and relevant data, is not just helpful, it's practically a prerequisite for the subsequent RL phase to succeed and remain stable, especially in these sparse reward web environments. RL needs something good to build upon.
Okay, and how did it fare when validated against the top-tier proprietary systems? They use the DeepResearch bench for that, right? Which specifically looks at complex info retrieval and generating a final report.
Yes, and it held its own remarkably well. The 30B A3B agent scored 48.9 overall on that benchmark. For context, that placed it second, only marginally behind the reigning champion at the time, Gemini 2.5 Pro DeepResearch, which scored 49.7. And the authors were quite transparent about this small gap. They attributed it likely to their training focus, which heavily prioritized maximizing the core retrieval accuracy and the synthesis capabilities, getting the facts right, finding the evidence.
Less focus on making the final report sound polished.
Exactly. They put less optimization effort into the final stylistic quality or the presentation layer of the generated report compared to perhaps some proprietary systems fine-tuned for that specific aspect. So the suggestion is that this small remaining gap isn't necessarily a fundamental capability issue in terms of researchability, but more a matter of final output tuning.
Interesting. Now, the training dynamics analysis, particularly looking at pass at 1 versus pass at 3 in Figure 6, this seems to offer some really deep insight into how the RL stage actually improves the agent's performance. And it seems to differ based on task complexity.
Yes, this distinction is incredibly important, especially for thinking about how we should benchmark future agents. Let's break it down. For the really complex benchmarks, like BrowseComp, they observed that both pass at 1, which is solving the task correctly on the very first attempt, and pass at 3, solving it correctly within 3 attempts, rise concurrently and significantly during the RL training phase.
Okay, so both metrics go up together. What does that tell us?
It strongly indicates that on these hard problems, the RL process is genuinely expanding the model's fundamental problem-solving capabilities. It's not just making the agent luckier, it's actually teaching it new, correct ways to solve problems, creating successful solution paths that simply didn't exist or weren't reachable by the initial SFT policy. It's learning new strategies.
But then when you look at the results on simpler benchmarks like XBench Deep Search or GAIA, the pattern is different. They see a big improvement in pass at 1, but only a very marginal gain in pass at 3.
Exactly. On tasks that are already well within the model's base competence after SFT, meaning pass at 3 is already quite high to begin with, RL's primary role seems to shift. Here, the big jump in pass at 1 suggests RL is mainly enhancing sampling efficiency. The agent likely already knows multiple correct ways to solve the problem, but RL teaches the policy to more reliably and confidently select the optimal path, the pass at 1 path, right from the start.
So it's less about learning how to solve it and more about learning to pick the best solution path first time, improving reliability and confidence rather than raw capability.
Precisely. It's a crucial distinction. On complex tasks, RL builds capability. On simpler tasks, it primarily builds efficiency and reliability in selecting among existing capabilities.
Fascinating. Let's also touch on the policy entropy dynamics shown in Figure 7. This looks quite counterintuitive if you come from a classical RL background, right? The policy entropy, which measures randomness or exploration capacity, stays consistently high and seems to oscillate throughout training. There's no clear downward trend towards a deterministic optimal policy like you might expect.
It is quite striking. In many standard RL tasks, especially in games or simulated physics, you expect entropy to decrease as the policy converges on the optimal strategy. But here, it stays high. The hypothesis put forward in the paper is that this sustained high entropy is a direct consequence of the non-stationary nature of the environment the agent interacts with, specifically the real-world web components. Think about it. External factors like search engine rankings, website content, API availability, they don't follow a fixed, stable distribution. The state the agent observes is constantly shifting in unpredictable ways.
So the environment itself prevents the policy from ever settling into one fixed, low-entropy strategy.
That seems to be the interpretation. The inherent volatility and non-stationarity of the web essentially force the policy to remain robustly adaptive. It needs to maintain a high exploration capacity just to cope with the changing world.
Yeah.
And arguably, for a real-world research agent designed to handle novel situations, this sustained adaptability might actually be a desirable trait, not a bug. They didn't even need explicit entropy regularization.
We also saw, unsurprisingly, a clear positive correlation between accuracy and increased context scaling, going up to 128K, though they noted most successes happened within 64K. But perhaps more telling was the comparison back to V1. The V2 architecture, even restricted to a 32K context, still achieved 16 accuracy on BrowseComp EN. That's a huge jump over the V1 agent, which was based on a much larger 72B dense model.
Yes, that comparison really underscores the main theme again. It highlights the profound impact of the improved data, Sailor Fog Q AV2, and the refined training pipeline, SFT plus dual environment RL, on enabling effective tool use, far outweighing the brute force scaling of the underlying model from V1. Methodology trumped parameters.
Okay, theory and aggregate results are one thing, but let's bring this home. We really need to spend some time on the case study walkthrough they provide. It's the form factor Inc. example, a complex query from BrowseComp that took the agent 29 steps to solve. This really illustrates the kind of sophisticated, almost human-like research process the agent learned.
Absolutely. This case study is gold. It makes all the abstract concepts concrete. The challenge, as you said, was to identify a specific company based on a set of quite diverse and tricky clues.
Let's list them. Find a company incorporated in Delaware where the founder became chairman effective Q3 2008 that had specific different revenue concentrations from its top customers in 2005 versus 2006 and was involved in a $1.5 million class action settlement related to overtime pay. That's a lot to juggle.
It really is. And the agent's first move, step 1, was critical. Clue decomposition and structuring. It didn't just treat that query as a single block of text to dump into a search engine. It intelligently broke it down into 5 distinct verifiable conditions. It created an internal structured representation, like a checklist.
That structured approach seems essential for tackling multi-constraint problems.
Definitely. Then, its initial attempts, steps 2 through 7, involved more generic searches based on some of the clues, like the dollar amount or incorporation state. But these were, as the paper notes, unproductive. Searching for $1.5 million settlement in 2015 just returns too much noise.
And this is where a less capable agent might get stuck or loop endlessly.
Right. But the WebSailor V2 agent demonstrated the crucial ability to recognize this lack of progress and perform strategy adjustment. It realized the initial keywords were too broad, too common, and it needed a more targeted approach.
Which led to the breakthrough moment.
Exactly. Steps 8 and 9 mark the identification of the golden clue. The agent seemed to reason, implicitly or explicitly, that the leadership change to the specific timing of the founder becoming chairman in Q3 2008 was likely the most unique and temporally constrained piece of information among the clues. So it constructed a highly precise, almost natural language query targeting this specific event, Something like founder will become chairman effective third quarter 2008.
Hmm.
This incredibly targeted search immediately surfaced relevant press releases pointing directly to FormFactor Inc. as the likely candidate.
Okay, so it found a promising candidate, but it didn't just stop there and declare victory, right? The next phase, from step 10 all the way through 28, was all about rigorous verification.
Rigorous systematic verification. This is what really impressed me. The agent didn't just accept FormFactor based on the one clue. It systematically went back through its internal checklist and used the other 4 clues as verification steps against this candidate.
So what did that involve?
It involved multiple tool calls. It used search to find official Delaware incorporation records to confirm the incorporation date matched. Then, most impressively, it targeted financial information. It specifically searched for SEC filings, like 10K annual reports for FormFactor. It needed to verify those exact, tricky revenue concentration figures. 3 customers accounting for 47.3% of revenue in 2006, and 4 customers accounting for 72.8% in 2005. And the case study shows the agent successfully navigating the SEC documents using the visit tool, likely leveraging its summarization, to find and extract these precise figures confirming the match.
Finding specific percentages from different years deep within financial reports that requires sophisticated document understanding and targeted search.
Absolutely. And the final verification step was the class action settlement. It again used targeted search, confirming that a suit involving overtime pay was filed by a former employee, certified around 2016, and ultimately settled for exactly $1.5 million in 2017, fitting the clue perfectly.
Wow. Only after methodically checking off every single one of those 5 distinct, complex clues involving numerous searches, document visits, and synthesis of information across steps. Only then did it proceed.
Only then, in step 29, did the agent execute the final answer action, constructing a coherent, logically structured response that presumably cited the evidence found for each clue.
That form factor case study, yeah, it really feels like the ultimate empirical proof. It demonstrates that this whole pipeline, the data, the training, the agent framework, successfully produced an agent capable of executing a research process with a level of rigor and multi-step reasoning that genuinely approaches, or maybe even exceeds in persistence, what a skilled human researcher would do. #tag outro.
Okay.
So, wrapping this up, what does this all mean? I think the WebSailor V2 paper stands as a really profound contribution. Why? Because it demonstrates achieving competitive parity, getting right up there with high-end proprietary systems, but using only a moderately sized 30B MOE open source model. And crucially, this wasn't accomplished just by throwing more parameters at the problem. It was achieved through meticulous, really thoughtful, top-to-bottom system engineering, specifically focusing on the data distribution and the stability of the training environment.
Absolutely. And if we have to synthesize a final key takeaway, it really has to reiterate the paper's core conviction, which they backed up empirically. Constructing a high-quality autonomous agent, especially one for complex tasks like web research, is fundamentally a complex system engineering challenge. They proved quite convincingly, I think, that high-quality data exemplified by Sailor Fog QAV2, with its focus on structural complexity, cyclic graphs, and richer uncertainty definitions, combined with a stable, robust training environment like their dual environment RL framework with its fault tolerance, are demonstrably more critical factors for achieving success than the specific underlying RL algorithm you choose, or even the sheer parameter count of the base model. The foundations matter most.
Which leads to a really interesting closing thought, maybe something for you, the listener, to mull over. We saw that divergence in the training dynamics, right? Where RL seems to primarily enhance sampling efficiency, pass at 1, on simpler tasks that the SFT model could already handle, but it fundamentally expands problem-solving capability, pass at 3 rise, on the really complex tasks. So the provocative question is, how should we as a community formally design and maybe standardize future benchmarks to more clearly distinguish between these two effects? How do we measure the true expansion of a model's intrinsic reasoning capacity versus just improvements in its solution sampling efficiency? Getting that distinction right seems crucial as we try to accurately measure genuine progress towards more capable AI, maybe even AGI.
That's a critical question for the field moving forward. The focus really needs to shift from just, can the agent solve the task, to how reliably can it solve it, why, and is it learning genuinely new skills, or just becoming better at picking the right skill from its existing repertoire?
A provocative thought for the road, indeed. Absolutely. Well, thank you for joining us for this deep dive into the impressive engineering behind WebSailor V2. A lot to think about there.
My pleasure. Until next time.